Now that we've got the graphing of simple harmonic motion down, it's going to be useful for us to be able to write an equation for that. We said yesterday, or we said in the previous video rather, that this curve represents a sine curve or a cosine curve. They're the same shape, they just have different initial values. One shifted over 90 degrees or pi over 2 to the right from the other one. So we can start with the assumption that if I want to write an equation for this graph, it's going to take the form of either x of t equals some constant a times the cosine of some constant omega times t, or x of t is equal to the constant a times the sine of omega t. Okay. We'll talk about what a and what omega represent here in just a minute, but even without understanding what those values are, we should be able to put together an equation for this. So first off, we need to decide whether we're going to use sine or cosine. So for that, I'm just going to look at the initial value here, and we've got an initial value of 0, which is corresponds to the sine function. Sine of 0 is also 0. If it had a maximum value there, it'd be cosine of 0 is at a maximum value. If we were shifted off so we don't have a 0 or a maximum or a minimum at a time of 0, we'd have to add a term into these equations to shift that graph, and we usually write that as plus phi. But since this one we have 0, 0 as our starting point, we don't need to worry about that. So let's start with the assumption then that it's going to use the sine curve, the sine function. We have some function of time that involves sine. X of t, x as a function of time, is equal to a times the sine of omega times t, where t should stay as a variable, and we should set this up so that this equation gives us this graph. Well, first off, let's look at what a would be. So the sine function has a maximum value of 1, and it has a minimum value of -1. So if we look at the maximum and the minimum values of this graph, we should be able to tell what coefficient we need to use there in order to make this work. And I realized that I kind of chose a boring scale for this, so I'm just going to change the numbers on the scale a little bit here. Let's make this 0.5 and this one -0.5, just so that we don't have ones in there that are going to drop out, and we're going to forget that they're there and get all confused. So we see here that we have a maximum value of 0.5 and a minimum value of -0.5. So that tells me that when I multiply my maximum value of the sine function by a, and the maximum value for the sine function is just 1, I need to get a value of 0.5. Or in other words, a times the sine of, when does sine have a maximum value again? Yes, it's pi over 2 radians, or 90 degrees. Just as a heads up, we're going to be getting into things where the convention is to use radians. We've been using degrees a lot so far, but radians are kind of the way things are usually written for this stuff. So get back into that mode in your calculator and in your head. A times the sine of pi over 2, that's the maximum, the time when the sine function has a maximum value, that has to equal 0.5. That's going to be this point right there. And so from that, I know that a times the sine of pi over 2 is just 1, so that's equal to 0.5, so a is just equal to 0.5. Okay, so we're making progress then. So x of t, we know is going to be equal to 0.5 times the sine of omega t. So now we just need to figure out what the value for omega would be. And for that, we're going to look at how much time it takes on the x-axis here, how much time it takes to complete one cycle. So it looks like with this one, I've got one cycle takes place in, well, I can do that here to here. That's my value for t. I can do that here to here. That's my value for t. Whoops. Went a little too far with my line there. There we go. There to there is a value for t. Wherever you want to measure it is fine, from one point to the next identical point. And it looks like here we've got 0 on the left end and 3.2 on the right end. So our period is 3.2 seconds. So I'm just going to make a note that period is equal to 3.2 seconds. Okay, so in the 3.2 seconds that goes by, we have one complete cycle. Now, one complete cycle in terms of radians, when I do the sine function, that needs to be 2 pi. So t in terms of radians has to be equal to 2 pi. Okay, so now I need to figure out, what conversion or what relationship can I implement here to get it so that when I have a value of 30.2 seconds, my sine function is going to give me my value of 2 pi inside here. So when t is 3.2 seconds and I've gone through one period, this whole function should be equal to 2 pi. So I'll just put that in here. So omega times 3.2 seconds should give us a value of 2 pi. So the sine of 3.2 seconds is going to give us just 0. Or sine of omega t, where t is 3.2 seconds, gives us 0. So omega then is just going to be equal to 2 pi over 3.2 seconds. Or as a decimal, that's going to be 1.96. And that's, let's see, radians up top and seconds on bottom. So that's radians per second. All right, so now I've got A and I've got omega, so I can write my equation. X of t is equal to 0.5 times the sine of 1.96 times t. All right, and let's just double check our equation, make sure we have it all right. So we'll use our graph, we'll make a prediction. So according to this graph, at a time of 4 seconds, we have a position of 0.5. So let's just plug that into the equation here. So x of t, x of 4 seconds, is equal to 0.5 sine of 1.96 times 4. And so x at a time of 4 seconds is equal to 0.5 times sine times 1.96 times 4. And we get, we get a crazy number because I didn't take my own advice and put my calculator into radian mode. But now that I have, I get a value of 0.5 meters. And that was what we expected right there. Okay, so our equation then, 0.5 sine of 1.96 t. Now, what are A and omega? Well, A, I think you probably recognize. A is just this distance right here, or this distance right here, which is the amplitude. And then omega, which looks a lot like a W, lowercase w, just make it nice and curvy there. Omega is what we call the angular frequency. The angular frequency, and if we look at the units for that, that kind of makes sense. We have units on omega of radians per second. So the per second part, that tells me, oh yeah, that's like a frequency thing. And then the radians, well, that's an angle thing. So angular frequency is what omega represents.